So let's welcome Joel, who is going to tell us all about printf, what it means and how it's used.
Thank you, Patrice. So I'm going to jump right in because we don't have much time. So one thing I love about CS, and I hope you're in the same case as me, is that before being a computer scientist, I'm an avid user of computers. And so all through my education and up until actually now, every time I discover how something that I've been using works, I have those aha moments, like, that's how it works. And so when I was asked to prepare a lecture for this application, I thought like, okay, I want to share one of those aha moments with you. And so I got to thinking and had to be accessible, like something that people would know, but at the same time also interesting for faculty members who like know a lot. So, and I chose printf because everybody knows that. We've been like using it. That's pretty much like every second slide of every programming class in C, like the famous Hello World. So everybody who knows programming has been confronted to that at one point or the other. And yet, I don't think many people actually got to implement their own printf, unless you would code your own operating system, which is pretty rare, hopefully. So actually, like in this example, we don't really have the aspect of formatting because we only have a string that will be sent to the screen without further processing. Another common example is to actually use placeholders in the string that say, oh, actually in this location, I would like this placeholder to be replaced by one of the arguments. And so the very common placeholders that we know are like %s to be replaced by a string, C to be replaced by a character, or D to be replaced by a number, right? Printf is actually like really, really powerful. We can get into some more interesting examples. Who knows %n? Seriously, no one? %n is actually the only placeholder that works backward, in the sense that here we're not printing anything. It's printf that is giving us back something, some information. And so here what %n does is that it will assign the number of characters that have been printed up until the %n, and we'll put that in the address of the variables that we're giving. Here you see that we're only printing one character, which is a space, and then we have the %n, which means that after this statement, I will be 1, because printf has printed only one character. We can get into even more complicated stuff. I can like print a string, and then with \b, actually like erase, go back, have a backspace within my string, and then like rewrite the last character. And even like I can send some special codes that the terminal will actually understand and change the color, or like the font. I can switch from a normal font to a bold font, this kind of stuff. So actually when you see the computer boot and you see that some stuff are appearing in colors in the terminal, that's the kind of specific sequence that would be sent. Yes?
So what's the point of %n? Where do you use it?
The %n?
Yeah, what is the use?
So I know that one use is to hack programs, to like do like stack attacks, and I'll talk about that a little bit later. An actual use that's not trying to hack an application, I have no idea. So yeah, so actually, as I was like preparing this lecture, I wanted to kind of trace like, okay, this formatted printing, like where does that come from? Is it something that came with C or that existed before? And I was actually very, very surprised to see that like it's not recent at all. It came with Fortran 1 Sorry, but I'm talking about it. And it was even part of the very first version of Fortran 1 back in the mid-50s, where they had 32 different statements in Fortran, including this very specific statement format, which would be referenced by a write statement. So here you see that the write statement essentially says like, okay, we're going to write on tape number 6. Don't ask me what it is. I think it's like, oh, I want to write maybe on the screen or something like that. Then we give the number of a label, and you see that it's the same number that's associated to the format line. And then we'd say, okay, we want to print integer A, integer B, integer C, and floating point number area. And then completely separately, we have this format statement that actually indicates how do we want to print those variables. At the time, they didn't have strings, like they didn't have proper characters with double quotes. So they would use something called Hollerith constants. And you see here that like the for h actually tells the compiler, actually after the for h, I have 4 characters. And you can count them, like I have a space, then a, then equal, and then a space. That's 4 characters that the compiler will recognize. Then we can print the first variable, a, as an integer on 5 digits. Then I have 5 characters, space, space, b equals, and then I would print b on 5 digits as well, and so on. So I put like the translation in C just to like give you some idea. About like 10 years later, came this other language called BCPL, which I believe evolved into the language B, which strongly influenced the C language. And so here, for the first time, we have a statement that actually combines writing and formatting. And here you recognize that the syntax gets really close to what we know. We have a string within double quotes, and we have here like, okay, I want to print an integer on 2 digits, so we have this idea also of filled with. And here you see one thing that's different is the star n instead of a backslash n to say, okay, I want to have a new line. And finally, a few years later, in the early 70s when C was released, we got the syntax that we all know. And I have no take on that, but it seems like it was a really good syntax that made consensus among everybody because it actually evolved, like printf evolved into its own Unix tool. You can type that into a terminal. And many other languages implemented their own printf with also the same syntax. Okay, so now we understand printf is fairly powerful and versatile. And we understand where it comes from, this idea of printing formatted strings. But actually, why do we need to print? And I sort of separated that into 2 different aspects. The first one is like for output, because as human being, like it's nice to have some feedback on what we see. There's almost no program that doesn't show you something. You have programs that don't take any input because they would run already on input that's kind of prefixed, but I don't know of any program that doesn't give something back to the user. And even in the Unix world, the output of a program can become the input of another one. So it's actually also how programs talk to each other. That's how they communicate. Another kind of separate aspect is the debugging or like introspection. So here, like getting some output from a program to actually understand what it's doing and making sure that it's working as planned. And for example, in the very early stages of a computer booting, it's very interesting to have some information about that, even before the screen is up, even like right when you start having the first few lines that are executed by the processor, already have some feedback to see what's happening. So what do we print actually? that I'm afraid I cannot really like delve into that so much. So it's kind of a black box. I'm just going to summarize that in 3 steps. You have a program, it's calling printf. The characters are going in the kernel in this insanely complex piece of code that has multiple layers. It must be like multiple dozens of thousands of lines in the Linux kernel, to the point that even some very famous Linux kernel developers are scared about this piece of code because it's so complex. And somehow, in the way that we know it, like on my laptop, for example, it gets back out of, like, back to user space, back to an application in the terminal application, and we get the display in this terminal application. So that's the way that we know it most of the time. What happens when we are on a computer that either doesn't even have a screen, like an IoT device, for example, or how do we get some output before the screen is up? Like on my phone, if the screen doesn't have a driver yet when the phone boots, like by the bootloader, say, how do I get some Intel? If I'm developing the bootloader, how do I get to that? So here, the other way that a printf can actually be transmitted to someone who would be listening or would be interested in knowing what's happening is that the characters can actually go outside of the device and be sent through an actual serial device or an UART. And that's very simple. Like I just need a couple of wires going out of my device, and I can send my characters as impulses of zeros and one. And whoever wants to listen can listen. And I have to say, like, it kind of blew my mind personally to understand that almost every, I would say, computer, like device that contains a processor and executes code actually always has a UART, because it's the most basic, reliable communication channel you can have. And even on my phone, this very phone, I got the schematic on the Sony website. If I open it, on the back of the phone, I have some connectors to which I could solder wires, plug that into a terminal, and actually get some printf that the phone is doing, probably right from the boot. So it's very useful for debugging when the screen is not up. Very useful for hacking as well. So here, like I found some screenshots for the PS4, like different version of the PS4. Hackers who are trying to like replace the software that's running on the PS4 and maybe run Linux onto it, they are looking hard on the motherboard of the PS4 to actually find those connectors and understand, oh, that's the UART. Like those are the connectors from which we can get some insight on the very early firmware that's running, and maybe get to discover that there is a backdoor somewhere that we can exploit. And even on the controller, I'm sorry for the screen, like it's very tiny. I feel like it's not very readable, but even on the controller, like you see this guy who like just removed opened the controller and soldered some wires outside to have some of the printfs of the software that's running inside of the controller. So now let's talk about implementation. How do I get to having my printf saying like %s, %c, %d, to actually having something that's displayed in the string? And for that, we need one function. It's really like kind of at the heart of everything, which is put char. I have one character, one ASCII character, and I need to transmit it, either like to print it on the screen or like to send it through this serial port. So here we're assuming that we would send it to a serial port. And you see that actually the implementation of putchar is kind of a device driver. I'm really like talking to the UART device and giving my character that the UART device will then transmit onto those TX and RX pair of wires. So if we have this function as kind of the cornerstone, like at the heart of our implementation, how do we build printf on top of that? If we have a string that's very simple, that doesn't have any placeholders, then it's actually fairly simple. My printf function is merely just a putS. I receive a pointer on the first character, and then I send this character through putchar, and then I go to the next, and I just like iterate through my string up until I find the null terminator, and then I'm done. And all of my characters have been sent. That's without formatting. If I bring in formatting, then much more complicated, because then it means that when I look at the format string, so the first argument, I have those placeholders, and I have to replace them with the corresponding argument. Printf, as you know, can have a different amount of arguments. I can have minimum one argument, just a string, no placeholder, and I'm just going to print that. It's kind of like the putS. Or the format string will actually tell me how many arguments I'm supposed to have, because all of the placeholders have to be replaced. And then I need to have all of those arguments following. So we need to learn a little bit about variadic functions in C. They're actually not that complicated, which is pretty fun. So the first thing that I need to include is this std_arg, because that will give me access to some of the functions to work with those variadic functions. Then here I'm showing you like how would I use that. So here it's a very simple function. We would assume that the first argument would give us the count of arguments that we're supposed to receive and sum. Like the whole idea here is to have a variable number of arguments that we want to all sum together and return the result. So here you see the way that we're using it is to say, like, I have 3 arguments, I have 3 integers, 10, 20, and 30, and I want to sum them all up. Or with the same function this time, I have 5 arguments, 10, 20, 30, 40, and 50, and I want to sum them up and return the result. And so on the side of the function, I know that I receive count as the first argument. That's a given, like I know I'm receiving that. And then comma and dot, 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 because I don't know how many are coming afterwards. And I know that like I'm returning the sum of all of them. So how do I implement that? I have to declare this like very special variable of type VA list, variable argument list. That's given to me by the std_arg.h header. And then I have to tell the compiler, okay, so my variable list of arguments is actually located after count, count being the first one. So I initialize this AP variable after count. And then I can go through the number count that was given to me. So either like, oh, sum up 3 integers or sum up 5 integers. So I know how many I need to sum up. And so I can have this for loop that goes from 0 to count. And at every iteration, I'm picking the next argument out of this list by calling this VA arg, saying like out of the list, I want an int. I want to extract an int. And so every loop, every iteration, I'm going to pick the next one. And in this example, I pick the next one that I get as an integer. I sum it up to the current sum. And at the very end, after having cleaned up this variable argument list, I can finally return my sum. So here, we're going to try something. We're going to try to like implement our own printf in the way that actually supports a few of the basic placeholders. So let me share my screen with you. if that works. Okay, so let's okay. So it's a very tiny screen, it seems. I hope you see something here. That should be enough, right? Okay. So here I sort of like prepared a little skeleton that only kind of implements the put s. You see here I'm getting the string and I'm just like looping through all of the characters and I'm sending them to putchar, and putchar will like either like put them on the screen or like send them through the UART. So say again?
Can you increase the size of the font?
I could try. That's kind of the maximum that I could do, otherwise we're not going to see anything. So if I make this one, okay, it's already up to date, and I run it. So here you see that I have kind of a basic printf that doesn't have any placeholder, and then one that has %s, %c, and %d. If I run that, I have a printf that actually doesn't interpret any of the placeholders. It's just like, just send stuff to the output. So how do I get to support those placeholders? Well, I have to transform my function. So I know it's a variadic function. So I know that like I need to declare this VA list AP variable. I need to initialize that VA start. I know that like my variable list of argument begins after the first argument, FMT. And here I can say AP. And at the end, I know that I need to clean up everything like that. Okay, so here I'm dealing with the variadic side of this function. Then instead of my while loop where I iterate through all of my characters, I have to detect if I'm the regular character or if I'm hitting one of the % sign, which would like imply placeholder coming. So if the current character is not a % sign, then I can just print it. I can just, well, actually I can just send it to putchar and then continue to the next. If it is a % sign, then I know that a placeholder is coming. So the % sign I can actually drop. I'm not interested because now I've detected that there was one. What interests me is what comes afterwards. Is it a C, a D, or an S? So I can go directly to the next one and then have a switch case on what the next one is. And so here I can, I will have 3 scenarios. We're just going to try to support. So let's start with C. Then we have, we're going to try to support S. And we're going to try to support D. And hopefully that should be enough to get us going. I also know that if I have to match those 3 placeholders, it means that I'm going to have to fetch the next argument out of my variable list of arguments. In case of a character, I will need to fetch the next argument as a character. If it's an S, I will need to fetch the next argument as a car pointer. And if it's a D, as an integer. So I need, up there, I need 3 arguments. I need a character, I need an integer, and I need a car pointer. And I know that every time when I hit one of my cases, so the C, I'm going to have to say C equals var arg of AP. And so here it's kind of weird, but I cannot actually say I want to read it as a char because the character that's pushed into a variable list of arguments is actually promoted to an int. So I have to read it as an int. The S, I will go pick the next argument as a car pointer. And the D, I'm going to go get it as an int. OK, so at this point, it's not going to work, but if I So what's wrong here? Okay, that's the opposite order. Let's try again. Whew. Okay. So here at least like things are starting to work. Like I'm starting to like get into what I'm supposed to do. Except that actually after consuming the character that's part of the placeholder, I also have to skip away from it. So, and that's why we see that on this side, I'm still printing the S, C, and D, which shouldn't happen. So at the end here, I have to like increase my car pointer by 1. If I try again. Okay, now I was able to actually remove my placeholders from the string that I'm printing, except that I'm still lacking what they should be matched with. And so that's the code that I'm going to add right now. So if I'm matching a character and I have this character as C, how do I print it on the screen? I just give it to Pucha. Very simple. Let's try. I have my A, capital A. That's new. What about the string? So here I get a car pointer. I have access to this putCar function. What do? Very simple. I just have a kind of putS situation where I just need to like go through this string until the null character and get to and print the current one and jump to the next one. So here, now I'm able to like match the %S, the %C. Now more complicated, I need to match the %D. And here it's kind of tough because I'm getting the %D as an actual int, but I need to send characters. So here I actually need to convert my number into characters that I can send to Pucha. There are like different implementations. The one that I chose is very easy. We're going to create. Oh, this one doesn't work. We're going to create a buffer. Can you guys see or not so much? Can you guys see? No? Oops. Oh. So I'm going to have a buffer here, a car buffer of, say, like 10 characters, and say I have the number like 300.
Someone has, you can use it.
Ah. Thank you. Oh yeah, much better. Thank you so much. Okay. So we're going to make a buffer of, say, like 10 characters. So this buffer is a buffer of characters because eventually like that's what we're interested in sending to Pucha. And so say as an input we'd have the number, well, like 45. And so that's an int. You guys know how to convert digits to characters, right? You try to isolate the 5 by using modulo 10. And once you have the 5, you can add it to ASCII char 0, and you get the ASCII character that corresponds to 5. And so once you have that, we can put it in our buffer. And so the first thing that I would put is 5. And then I would go on to the 4, and so on with all of my digits. And I'd be able to like reconstitute all of the characters. And that's where like the tiny trick happens. If I have a buffer, I have like access to the first cell of it, like the first item. But I can also maintain a side pointer that will go forward as I'm adding more characters. So I will have another pointer that always points to the next one. I'm calling end. Once I'm done doing the translation from integer to my characters, I'm in this situation. And what I will do is actually like have end, rewind, go backward from the very last character that was converted back to the first. And I'm going to send that to Pucha in that order, and I have actually 45 be printed. So that's kind of the algorithm here that I'm going to try to use. So first step, we need to like convert D to an array of character. So let's make a character a buffer of, like we said, 10. Let's have a pointer end that originally points onto the buffer. So at first my end will be there and will evolve. And now I can actually go through my number and do the modulo 10 to extract the digit, and then divide it by 10 to go to the next digit, and so on. So I'll do, here I'll put that into, I'll do like a lot of things. Well, actually, let's do things separately. So at first, I'm going to access what the cell that n points to, and I'll put D modulo 10 plus the ASCII character that corresponds to 0, just like I showed here. And then we'll go to the next one for the next iteration. And at the same time, we'll divide D by 10. Once I'm done with that, I'm in this situation. I'll have n, the pointer n, point onto the next one, and I'll have all of my characters be backward in my array. And so here I can now like go back from end to buff and send that to Pucha. So here, while end different than buff, I'm going like all the way backward, and I can send to Pucha. Well, actually, I can have my end pointer like go one backward, and then well, actually, now I think I need to do it all in one statement. And so here, hopefully, I'm able to actually handle 45.
So what if the number D was 0 minutes and instead of 45?
What if it was 0?
Yeah.
Let's try. Do you want to put 0 here?
Yeah.
Nothing happened. There's a bug in my program. Happens. Well, I guess I'll have some fixing to do for the next one. But you get the concept, hopefully. So let's get back to the lectures. Okay. Well, actually, like, if I can find my, okay, I'm back. I have a slide that might answer your question. I mean, not your question, but your observation.
So actually, why did you assign 10 characters?
Say again?
Is there some special value to the buffer being 10?
Oh, no, I mean, okay, so 10 is the maximum amount of digits you can have on an int that's on 4 bytes in base 10. Probably you should be more careful when you allocate your buffer. There might be some other considerations, but here I just wanted to aim for the simplest implementation that actually doesn't exactly work. So, so yeah, yeah.
It doesn't work.
Say again?
I'm good at writing ones that don't work. I can write a lot easier.
Oh yeah.
That's to not work in an interesting way.
Well, that's mine just don't work. So that's.
And it doesn't mean it's not interesting. Why it won't work.
So, so actually, like the printf family is pretty big and pretty complex. Like you might recognize a lot of them between like printf, fprintf, dprintf that writes onto a file descriptor, the whole like sprintf to write into a buffer already allocated. a sprintf that writes into a buffer that's not allocated and that will be allocated by printf itself after discovering how many characters it needs, and so on. So it's pretty complicated. And I spent some time yesterday looking at like various implementations in the different C libraries that exist nowadays, from the GNU libc, and you see like the file that contains really the core code for printf is insane. It's almost 3,000 lines. It's very, very difficult to read because you have to like take care of all the specifiers, all of kind of conversions and everything. It's a pretty fine piece of machinery. The ulibc, microlibc, which is supposed to be a lighter version of the glibc, is still like pretty heavy. And at the end, we have a much more simple implementation, but this other very lightweight C library called Muscle that's only about 700 lines of code. So yeah. Another kind of interesting thing about printf is that there can be some security issues with printf, and it was very popular, like this kind of attack back in the 90s and early 2000s. It's called uncontrolled formatting string attack. So here, that's some code that you see. Maybe you don't see where the problem would be. Just to like give you a little bit of pointers, we're reading something from the user into a buffer, and then we're calling printf directly on that buffer. Now look at some other code that does almost exactly the same, but there's one line that's different. Instead of calling directly printf on the buffer that was supplied by the user, we're actually saying like, we want to print a string with %s as a placeholder, and that's what the content will be. And it actually makes a huge difference. Because in one case, if I try to take advantage of that, if I execute this program and I actually try to mimic a formatted string with %s, %s, or like some other stuff, here nothing happens. Because the string that the user gives is not processed. It's merely a buffer that will replace the placeholder %c. Now in the other case, if I supply the same input to the other program, I'm able to make it crash. Because here, printf will receive this string as the formatted string that it's supposed to interpret and that it's supposed to find the placeholders and replace them by something. Except that printf doesn't have any arguments to match all of those %s. So what it will do is that it will start picking stuff from the stack, which is complete garbage. I mean, or at least not relevant to what we're trying to do. And pretty soon, usually, we're going to pick something from the stack that's not an address, and we're going to try to dereference it to like interpret it as a string. Program is going to crash. So program crashing is obviously something that we don't want, because that can make denial of services. Like if you are able to make a web server crash, or these kind of things that can be bad. But even worse, because depending on the string that now we supply, we can get intel about the stack by printing the values that are on the stack at this very moment. And remember the %n from the very beginning, where we can actually have printf write something into memory? We can exploit that with a very carefully crafted format string. We can get printf to write at pretty much any location in memory. That'll be it for me. Thank you.
So how have they addressed that? That was a problem in the 90s and the 2000s.
By pushing for people to write this kind of code, and by not
So
having...
I can still do that over
Oh yeah, you could do that. Oh no, actually, no. Let me rephrase that, because full disclosure, I spent my entire Sunday not working on those slides, but trying to find a good exploit that I could show during this presentation. And there are a quantity of protections now to avoid that from happening. There are some protection around the stack, like the stack is kind of randomized, or like they put some canaries or some flags to make sure that the stack is not overwritten in an illegal way. They have the stack not be executable, which was not the case before. So before you could even like inject some code in the stack, a code that would say like kill the process and run a shell instead. So if you were able to hack an application that was running with root privileges, you would become root and have a shell, which was quite problematic. And finally, in the recent years, or let's say like the past 10 years, the kernel, every time that it loads an application, randomizes the layout of this application. So as an attacker, you cannot rely on having addresses, especially within the stack, be always the same from one execution to another. And to make this kind of attack, you actually need to know kind of like where you would like to write. So yeah.
So does that stop like the denial of service type attacks? Will the program still crash with all these? Will it just stop information from using?
Maybe from with the %fs like that, you would still be able to make it crash. Because that, yeah, it's very, I mean, you're essentially saying like, hey, there's a string at this address, can you print it? If there is a 0, then you're going to try to dereference a 0, and nothing else can happen other than a crash. So, hey.
Why is it called printf instead of print?
Because it's formatted.
Okay.
Yeah.
That's right, it's formatted print.
So I think my printf has a bug. So I try to scan a number and print it, and it gives me a different number. Is that possible?
What do you mean
I scanned in 0.1 and then tried to print it, and it gave me some slightly different number. Is that possible? Is that a bug in printf?
Ah, your printf, like on your computer, the one that's
I do a scanf of 0.1.
Of 0.1.
I printf %f, and then I get some other number, which is not exactly 0.1.
Well, point one doesn't have an exact binary representation.
You can now make that 0.1. I see. Thank you. I didn't know.
For what it's worth, when you're talking about the importance of output, when I was working on my PhD, I was trying to figure out what an optimizing compiler would do, because you had to write everything in assembly language. So it turns out if you have a program, I wrote this approximate program, and I didn't want to deal with the I/O part, so I didn't have any printfs in it. So the optimizing compiler just created no program. It was smart to say, you're not putting anything out. What's the point in doing it? You're not doing anything if you're not creating output. It's like, well,
That is interesting.
that's an optimizing compiler for you.
Yeah. Yeah.
So you spent a lot of time talking about the formatting side of it. Could you comment, at least from a high level, the intuition behind how the operating system part works?
You mean like the scary part?
Yeah, you showed the quote, but like, what's the intuition? From a high level, how does it work?
I'm not sure. Let me go back. Are you talking about this part or not at all?
Yes, this part.
Like this part?
Yes, this part.
So to be honest, it's a very, very complex part. When I ported Linux to this to another processor architecture during one of my postdocs, I had to create a kernel driver that would cover like the multiple layers, and it was a very simple driver because I had the very simple terminal device that would pretty much just be a UART, but still, like I think the file was at least 500 lines to actually provide a driver for many of the levels. I really couldn't like tell you again by heart because it was a long time ago, but it's a very complicated layout where like from the application part, when you do your printf, it actually goes to a /dev/tty kind of device, that at kernel level is like bound to one of the device drivers. And so you have the first level that like understands that actually it goes, since it's a file in the Unix file system, it would go to the VFS part first. Then the VFS would recognize like, oh, that's not a file, that's a device. So it would like send this to the device layer. And then we would recognize like, okay, it's a car device. So it would go to the car kind of subset. And then from there you would go at some point to like the TTY kind of layer. And this TTY layer has at least like 3 different levels. Because it's a TTY layer that can either like be a master TTY, a pseudo TTY, or a slave TTY. I mean, just like the terminology is insane. I can not really go much deeper than that.
Well, and is it often another thread or process this is happening?
That I think like depends. It depends on the.
It would be deterministic the order things got printed, but heavily non-deterministic how it would splice in with the surrounding.
I believe,
non-print
as far as I remember, it depends on the implementation. My implementation, for example, was very simple, so I think there was a direct link between like we receive a character, it gets printed right away to the whatever device. In some other implementations that were much more complicated, like other device drivers, they would have this kind of two-phase thing. Like we get a character, we put that in a queue, and later we'll have a kernel thread pick that queue and actually send it to the device.
And there's typically some. I just remember getting used to saying, okay, printf and then flush, printf and then flush, printf and then flush to make sure it gets out.
Well, actually, like the as far as I know, but I might be wrong, the flush only makes sure that everything is pushed on the kernel,
Okay.
but the kernel doesn't commit to like flushing that to the device at all.
So the C language does not specify when that character is going to show up on the screen. It doesn't
Nope.
guarantee in terms of.
I don't think so.
If you were a programming language designer and wanted to do like a more strongly typed variant of this, how would you?
That sounds like a tricky question. Rust? No. In all fairness, I'm not a very language-oriented person. I really like C. I think my students could testify on that. I'm very happy with C, and even if it's not strongly typed, just the idea that when I type C, I can actually run the code in my mind and knowing exactly what the processor will do, that's enough. Like I get what I want. Yeah, I don't know. Sorry, I don't have any like.
Definition of C, you didn't have any big variable argument procedures. And I found it very strange that one of the most common subroutines you would call can be written in a programming language. When was this rectified and how?
I'm sorry, I think I missed
How
your.
was it somehow fixed? I mean, when did variable arguments somehow appear in C?
The variadic functions, I don't know when it was introduced. I really don't know when it was introduced. That's a good question though.
Is there a way for a user to define their own percentage character?
Yes! You have so many good questions. So actually,
If I knew what you're talking about.
I started having a few slides about that, how to define your own placeholders, and I thought it wouldn't fit into the presentation, so I removed that. But there is a now deprecated, there are some deprecated functions from the glibc that allow you to have a callback function that will be called when a certain placeholder occurs. And I believe you can even overload some of the existing placeholders. And so if you have, say, like your own custom data structure, you define the printf function that knows how to display it. You kind of register that callback function with the printf infrastructure, and your function gets called when you just use like % whatever letter that you want.
Register it with the compiler, I suppose?
You register, no, it's something that happens at runtime. Like you register it with the libc. It's a function call, so that'll be registered at runtime.
So I guess if there are no more questions, we should thank again the speaker. And we hope to see you again on Thursday for new aspects of this time C++ library.